Topics in the History of Mathematics, MA 290, Cassette 5, Side 1. On this side of the cassette, you'll hear a talk on Descartes' programme, which relates to your work in Unit 8. The talk is by Tom Sorrell of the Department of Philosophy at the Open University and is entitled Descartes' Programme.
When Descartes died in 1650, he left behind many followers in a number of European countries. These Cartesians, as they were called, took up the program for a complete philosophy that had been outlined in Descartes' Principles of Philosophy. Descartes wrote that the principles contained all that was most general in physics, but that more was needed. Observations and experiments had to be performed, observations and experiments, Descartes said, that were too numerous and expensive for one man to carry out. In our own day, Descartes is not widely remembered as a natural scientist. He's known as a mathematician, and above all, as a philosopher, the philosopher who said, "I think, therefore I am." In his own eyes, however, his results in pure mathematics and philosophy were secondary to his findings in physics. Physics was at the center of the complete philosophy. As he put it in the preface to the Principles, physics was the trunk of a tree whose roots were metaphysics and whose branches were all of the other sciences, reducible to the three principal ones of medicine, mechanics, and morals.
Philosophy as a whole is like a tree, whose roots are metaphysics, whose trunk is physics, and whose branches, which issue from this trunk, are all the other sciences. These reduce themselves to three principal ones: medicine, mechanics, and morals. The highest and most perfect moral science, which, presupposing a complete knowledge of the other sciences, is the last degree of wisdom.
Because Descartes tended to regard the complete philosophy as largely his own creation, the trunk of the tree was not physics impersonally conceived, but rather Descartes' physics. Similarly, the branches of the tree were not medicine, mechanics, and morals simply, but Descartes' medicine, Descartes' mechanics, and Descartes' moral theory. His work in these derivative natural sciences, especially medicine and morals, did not really get beyond the preliminary stages. But he did write part of a medical treatise called Description of the Human Body, and there are the outlines of a theory of morals in his last full-length work, The Passions of the Soul, and in his correspondence with Queen Christina of Sweden and Princess Elizabeth of Bohemia. Although mathematics played an important part in his work, it is notable that no named part of Descartes' tree of science corresponds to it. As for metaphysics, the setting for the famous cogito ergo sum, or I think therefore I am principle, it's identified with the roots of the tree, the parts that, while fundamental, are out of sight below ground. Descartes thought of both mathematics and metaphysics as supports for natural science that were not, at any rate in their pure form, parts of natural science themselves. From mathematics, Descartes believed an inquirer could learn a certain logic of scientific discovery, that is, a certain method for relating unknown to known elements of problems.
He should study the logic that teaches us how best to direct our reason in order to discover those truths of which we are ignorant. And since this is very dependent on custom, it is good for him to practice the rules for a long time on easy and simple questions such as those of mathematics.
After mastering this method, an inquirer would be in a position to pass to the first part of philosophy, that is, to metaphysics.
Then, when he has acquired a certain skill in discovering the truth in these questions, he should begin seriously to apply himself to the true philosophy, the first part of which is metaphysics, which contains the principles of knowledge, amongst which is the explanation of the principal attributes of God, of the immateriality of our souls, and of all the clear and simple notions which are in us.
In metaphysics, he would discover indubitable principles from which it could be demonstrated that the human mind was capable of formulating a quantitative science of matter, or physics. I think, therefore I am, was the first of two principles necessary for the metaphysical demonstration of the possibility of physics. Descartes arrived at it by going through a thought experiment in which all conditions favorable to the formulation of physics were first imagined absent. The thought experiment stipulated that any inquirer's mind would be manipulated by a deceiving demon. This meant that no inquirer could trust his scientific observations or reasoning. Could such an inquirer in fact know anything? Descartes believed that even when in the grip of demonic deception, an inquirer could have some knowledge, enough in fact for getting the rudiments of physics. An inquirer could realize that if he was being deceived, then at any rate his mistaken thoughts were real. And if they were real, then so was the self who had them. In other words, the inquirer could know that if he thought, he existed. From the knowledge of the reality of his mind and of its contents, it was possible for an inquirer to deduce the existence of God as the only possible cause of some of his mind's ideas. And from his knowledge of the nature of this God, an inquirer could deduce the existence of the most general properties of matter, for ideas of these properties were placed in his mind by God, and no ideas with such a source could be of what was unreal. In this way, the subject matter of physics was placed beyond doubt, and the whole science could be erected on firm foundations, physics in turn supporting the rest of the sciences in the relation of a tree trunk to its branches. Descartes sometimes claimed to have carried out his scientific research in precisely the roots to branches order of his tree metaphor. That is, he sometimes claimed to have worked out first a logic, then a metaphysics and physics, and finally, when he was running out of time, the outlines of medicine, mechanics, and morals. Though it makes a good story, Descartes' account of his orderly progress through the sciences does not appear to fit the facts. Instead of working steadily through a sequence of investigations mapped out in advance, Descartes seems to have applied himself sporadically and to have made his way in a somewhat haphazard fashion, certainly not according to an agenda for a complete science. For example, it's known that in 1629 or 1630 he abandoned a treatise on metaphysics that he'd been writing for nearly a year. He came back to this book in 1640 after he'd completed a comprehensive statement of his physics. Between periods of work on physics and metaphysics, he took time out to return to pure mathematics and to refine his thoughts about what he called logic. And throughout the 1630s, he conducted experiments that contributed to his medical theories, theories that his official agenda called on him to take up last, or nearly last, in systematic research. The project that actually dominated Descartes' working life, and that revealed such order as there was in his researches, was not the hugely ambitious one of giving the public a complete science. It was that of composing a treatise on physics, and then preparing the ground for its release. In 1630, at the age of 34, after failing in several attempts to produce something that would establish his reputation as scientist and inventor, Descartes embarked on the formulation of a theory that would explain, among other things, the nature of light, the behavior of the planets, the properties of terrestrial bodies, and the physiology of perception and movement in human beings. Descartes divided the presentation of the theory into two parts and devoted a treatise to each. The second part, on man, would be a tailpiece to a text on physics entitled The World. When Descartes started to write The World in 1630, he didn't think it would take long to produce the statement of his physics. He proposed a timetable to himself which committed him to have the treatise ready for posting to Mersenne by the beginning of 1633. In the event it was not completed on schedule, corrections were still being made in July of 1633. Worse, when it was ready for press, Descartes heard that Galileo had been condemned by the Inquisition at Rome for teaching the doctrine of the Earth's movement. The World, Descartes' book, also contained a hypothesis of terrestrial motion, one that could not easily be taken out without spoiling the rest of the book. Fearful of suffering Galileo's fate, Descartes wrote to Mersenne in 1634 that he would not publish. From the version of the original text that survived and was published after Descartes' death, it's clear that in the book he stopped short of asserting the doctrine of the Earth's movement. Here he was helped by the literary form of the treatise. As in the Discourse on Method, which appeared 3 years after The World was suppressed, Descartes claimed only to be unfolding a fable, a story of the workings of an imaginary universe, though one that was to all appearances identical with the actual physical world. Descartes first invites his readers to think of the universe as if from some point in an imaginary space extending away in all directions, like an ocean as viewed from some point on it far away from land. Next, one is supposed to imagine God creating an unspecified kind of matter that completely fills every place in space. The idea of a perfectly full universe was one of the distinctive elements of Cartesian physics. Astronomical effects, such as the paths and speeds of the planets, were traced by Descartes to a circular motion like the action of a whirlpool in celestial matter. According to Descartes, the planets were swept round in a vortex centered on the sun. More locally, another vortex swept the moon round the Earth. The local vortex motion also explained why objects on the Earth's surface were not thrown off at a tangent while the Earth rotated. The whirlpool action would make all surface objects gravitate toward the center of the whirlpool, the Earth's center, just as, instead of being thrown off into space by their movement round the sun, the planets gravitated towards the center of their whirlpool. An expurgated version of the physics in the world was eventually published in the Principles of Philosophy, but that was not until 1644, nearly 10 years after the original theory was suppressed. Descartes' publications in the intervening years were designed to create an audience for the ideas he was holding back. The Discourse on Method and Essays, brought out in 1637, illustrated the fruitfulness of Descartes' technique of problem-solving in the sciences, a technique that he'd already used in the world. He was selective in revealing his results in the essays and showed only what could be done with the technique in the relatively uncontroversial areas of optics, meteorology, and geometry. Further applications of his method to cosmology and planetary movements were alluded to in the discourse, but not actually spelled out. Readers who were tantalized were expected to clamor for the release of the physics. A topic Descartes took up in the essay on optics was the behavior of light, specifically the phenomenon of refraction. It's simple enough to detect that when light travels from water to the air, the path of the light changes when it reaches the surface of the water. Once you have the idea of looking for a numerical relationship between the angle with which the light hits and the angle with which it leaves the surface, and you know a little trigonometry, it's quite easy to quantify this relationship. Today we call this relationship Snell's law, after Willebrord Snell, but there are other candidates for its discoverer. The English mathematician Thomas Harriot undoubtedly discovered this law before Snell, but he didn't publish it. Another candidate for its discoverer is Descartes, and although it is easy to think of ways in which he could have learned of Snell's work, it seems that he did not. So Descartes also has a genuine claim to being the discoverer of Snell's law. Descartes' approach arose from a natural question about the telescope. What shape should a piece of glass be if it's to refract light falling on it from the sun or a star to a focus? Descartes began by thinking the answer might be a conic section, as it is when the question concerns reflection, and it seems likely that in pursuing the question about refraction, he was led to discover Snell's law. But here Descartes' physics was in a mess. In his view, light traveled with infinite speed, but to explain refraction, Descartes proposed that light travels at different speeds in the different media, and, to make matters even worse, that it traveled faster in the denser medium. Fermat, who believed that light travels with only a finite velocity, and slower in denser media, was surprised to discover that, despite so many contradictory ideas, Descartes had nonetheless derived the correct law. But the study of refraction did bring Descartes one considerable success, and here he did marry his mathematics to his observations. He showed that light traveling in water will not escape if it meets the surface at an angle greater than a certain critical amount, but will instead be reflected back into the water. This is a simple consequence of Snell's law. By coupling this idea to the idea that a rainbow is produced when the sun shines into water droplets suspended in the air, Descartes was the first to explain facts about the rainbow which had baffled everyone before him. He could show, for instance, that the primary rainbow could not occur higher than about 42 degrees, nor the secondary rainbow below 51 degrees. Moreover, albeit by invoking a weirdly implausible mechanism, he could account qualitatively for the colors in the rainbow. Not only had no one done this before, but in so doing Descartes was the first to make the theory of color a secure part of the science of optics. Despite the success of the method illustrated in the essays with certain scientists, especially in Holland, Descartes' results proved insufficient for winning the endorsement of the Church. The publication of his metaphysical masterpiece, the Meditations on First Philosophy, was intended to win the theologians over once and for all. Descartes disguised the book as a piece of Catholic apologetics, confiding to his friend Mersenne that its real purpose was to provide foundations for his physics. The Meditations had the desired effect. Eventually, Descartes got the permission of the head of the Jesuit order in France to proceed with the publication of the Principles. The sanitized version of his physics in the Principles and the original version in the World are sometimes described as pioneering contributions to modern mathematical physics. Interpreted in a suitably guarded way, this claim is true. Descartes did help to substitute quantitative explanation for the qualitative explanations of Aristotelian or scholastic physics. In the qualitative Aristotelian physics, explanation consisted of tracing the observed properties of things to the natures that made these things belong to one natural kind, for example, tree, horse, dog, rather than another. The classification of things into kinds depended on qualitative similarities and differences not open to quantification. The background theory appropriate to this form of explanation assumed that nature as a whole was inherently ordered and stable, and that each kind of thing in it had a proper and characteristic behavior and development due to its nature. Thus it was proper to stones to fall to the center of the universe, because it was only there that a stone could realize its nature. Celestial matter had the purpose, by nature, of turning regularly and eternally in place. Acorns were naturally destined to develop into oak trees. Except for what happened by accident to observed objects, all of their behavior was in keeping with some underlying form or quality. Newly observed properties of substances had to be explained ad hoc, by adding to the qualities or forms that they were supposed to have by nature. Practitioners of the new quantitative physics changed all that. Instead of citing countless different forms or natures of natural kinds to explain observations, they were able to cite a few forms that were common to all kinds of physical objects: shape, size, position, number, and so on. They could thus claim to be using a kind of explanation whose generality and simplicity the Aristotelians could not hope to equal. Another advantage of this kind of explanation was its use of forms capable of precise measurement. Descartes, it must be said, did not often exploit this feature of quantitative physics. His version of Snell's law was the exception to the rule. For him, the mathematizing of physics usually meant the restriction of physical explanation to explanation in terms of the quantitative forms of size, shape, position, and so on. It did not usually mean the discovery and formulation of exact mathematical regularities in nature, though this was what was called for by methodological doctrines he developed in the 1620s. When it actually came down to doing physics, Descartes seems to have lost his early enthusiasm for thoroughgoing mathematization. So while he always identified physics with applied geometry, that is, with the science of interactions between bodies, considered as having dimensionality and speed only, he did not go as far as Galileo and Newton did in putting the theory of nature on a mathematical footing.